Okay, good evening to everyone. So today we'll be continuing this previous year questions from GATE Aerospace paper um, on jet propulsion topic. So in today's session, so I will be covering 2018 paper propulsion related problems. There are very few which is asked in 2018 compared to other years. So and also relatively easier questions on 2018. It applies to all the subjects. So 2018 was perhaps the easiest paper. So let us see questions one by one. So myself, Akshay, you guys already know. Okay, let us jump into the first question. The first law of thermodynamics is also known as conservation of. Yes, can anybody answer this? It's straightforward. It's a conservation of energy, right? So first law of thermodynamics, if I want to put it into a mathematical form, it looks something like, so in specific quantities, delta Q plus delta W is equal to dE. So here we know it's a conservation of energy principle. This is very straightforward. It is worth discussing individual parameters over here. So you see the individual mathematical symbols what we are using here has a specific meaning. So we use delta Q, delta W, whereas I use dE. So what does this actually indicates? So whenever I use a differential form such that dE, that is a point functions, right? So that means like if I have a system which undergoes a thermodynamic process, say from point 1 to 2. Okay, so if I'm representing in PV diagram or so, okay. So now, so from state 1 to state 2, so here I can find all quantities such as internal energy of the system, entropy of the system, and those kind of things, say E1, S1, and all, so on. So similarly at state 2, if I define them, so I can write E2, S2, etc. So I can write for this equation that once the thermodynamic process is taken place, so I can write the change in properties as like E2 minus E1 or S2 minus S1. It depends on the state of the system. It doesn't depend on the path through which the process is taken place. So those kind of variables are state variables. Whereas work or heat transfer, here Q is a heat transfer per unit mass, whereas W is work per unit mass. So these are not point functions. These are path dependent. So if I say like I have a process A which is going from 1 to 2 in this path, whereas process B which is going in this path, these two are different. So the work transfer or heat transfer are going to be different. Usually you can find out by integrating over this area under this curve that represents the work in PV diagram, whereas in TS diagram you can calculate the heat, right? So they are path dependent. So, and the one more important concept you have to understand here is work and heat are a transient phenomenon. They cannot be stored, but they can be converted from one form to another form through a internal energy change. Whereas energy that can be storable, right? So like we see like when you charge a mobile phone, you're storing a energy, kind of energy, and you'll be spending it once you start using the mobile phone. So you're spending that energy, so you can store. Whereas work or heat we cannot store, right? So the work and heat are the transient phenomenon which occurs as the system boundaries. So like work or heat, they will usually heat will transfer from system to surrounding or surrounding to system. Similarly, work can be transformed from one medium to another medium. Say, so take an example of a compressor, where you are converting the mechanical energy into a fluid's internal energy change to raise the system properties like pressure. You are raising the pressure in compressor. How? You are rotating a machine that will impart an energy to the fluid which is flowing through the compressor. You are transferring that energy into the fluid so that the internal state of the system changes, so that results in rise in pressure. So that is the transferable quantity. So they are energy in transit. So you can transfer the energy from one form to another form. So that's all this first law of thermodynamics says about conservation of energy. Energy can neither be created nor be destroyed. It can only be transferred from one form to another form, and it can be storable. That's important, right? Though we have this conservation of energy which beautifully governs the physics or thermodynamics of the process, but why even in the first place the first law is not sufficient to understand the process, because it doesn't give you the direction of the flow. That is why we introduce the second law of thermodynamics. This is kind of governs in which way the thermodynamic process has to take place. That is where the concept of entropy comes. So second law of thermodynamics is a combination of different statements, inequality statements and all. But in a nutshell, if I can say, it governs that the change in entropy of the system always going to be greater than or equal to zero. This is how the process has to take place. The entropy of the system cannot be changed in a way that it will go to it is going to decrease the entropy of the system. It is not possible. That's the idea of second law. So entropy is in a layman word, it's a order of it's a measure of disorderness in the system. So this is a very lame definition. You might have studied in your high school physics, but it's a kind of explains what entropy is. Okay, so just because this question is raised in the gate, so I'm just bringing in all the concepts which is relevant from thermodynamics perspective. Okay, so you can expect any different questions from apart from this also. Okay, so now we will move on to the next question. That is, in an ideal gas turbine cycle, the expansion in turbine is represented by option A, an isenthalpic process, option B, an isentropic process, option C, an isobaric process, option D, an isochoric process. Which one of these is correct? Option B, right? An isentropic process. So expansion process in a gas turbine engine. So we know ideal gas turbine engines, they work based on Brayton cycle. So if I have to draw it in Molnier diagram or TS diagrams, so I have isentropic compression, isobaric heat addition, isentropic expansion, and this is an open Brayton cycle. So the last process is not exactly important for us. It is not a closed loop or not a closed cycle. It's an open-ended Brayton cycle. So state 1 to 2 is compression, 2 to 3 is combustion, 3 to 4 is expansion. So expansion occurs in isentropic manner. What is an isentropic process? Isentropic process is a process in which the entropy does not change. It's also reversible as well as adiabatic, right? So this is a relatively easier options to pick, but as this question is asked, I want to bring in some concepts related to this process in a TS diagram. See, in an actual cycle, we really don't see an isentropic expansion, but still we assume it to be an adiabatic expansion. So the major difference in adiabatic and isentropic is the reversibility, right? Adiabatic process, still there is no heat addition or heat extraction, but it can be irreversible. So the process can bring in some irreversibilities, which will result in rise in entropy. So the second law, so if I have to put in an exact way, the change in entropy is part of due to a reversible process by some reference temperature plus ds irreversibilities. So this part can go to zero in adiabatic process, but still this part can exist. So that makes ds is greater than or equal to 0. So for pure adiabatic process, it will be ds greater than 0. For isentropic process, ds is equal to 0. So this is what happens. So there is some misconceptions among the students. Can a process be still have a constant enthalpy if the process is not isentropic? We can, right? This is a very interesting process. So there can be a thermodynamic process through which the entropy change, that is S2 minus S1, can still be 0, but it is not categorized as isentropic process. How can it be happen? So that is because if you see this ds is equal to delta Q reversible divided by T plus ds irreversible. Say I have some kind of a process in which this part is negative, this part is negative, and this is always going to be positive. This is the law of thermodynamics. I cannot say anything on this. It's an irreversible process. Once it is done, the entropy is always going to increase. So the net sum of these two can still be 0. So in that scenarios, still my S2 minus S1 is going to be 0, but it is not categorized as isentropic, because isentropic is the process in one which it is both reversible as well as adiabatic. This is clearly not an adiabatic process. It can be some isothermal process or something else, some polytropic process where heat transfer still exists, which results in a negative change in entropy, whereas the irreversible part of entropy change is positive. Net sum is going to be 0. It can still happen. So once you consider the entire system, it is still not violating the law of thermodynamics. It can be greater than or equal to 0. That is still valid. It's equal to 0. But the part of which is negative, the part of which is positive. So net sum is going to be 0. It can happen. Okay, that's one possibility. I'm not saying it's always going to happen. It's one of the possibilities. We can still have delta S0, but not isentropic process. Isentropic is a process which is defined as reversible as well as adiabatic. That is how we define it. I hope you guys are clear on this aspect. Okay. The stagnation pressure at the inlet and the exit of a subsonic intake are 100 kilopascal and 98 kilopascal respectively. The pressure recovery of this intake will be, it's a very straightforward question again. So I have a subsonic intake. How subsonic intakes would look like? It is any duct which has a diverging area for subsonic flow. The duct through which a pressure is changing to kinetic energy, or kinetic energy is changing to a pressure. So the diffusers are those ducts in which kinetic energy will be changing into a pressure energy or something like that. So in this case, some incoming P naught that is given to be 100 kilopascal, and I have exit P naught, say P naught 1, I will call it as 98 kilopascal. So what is pressure recovery factor? So pressure recovery is defined as the exit total pressure to inlet total pressure, say P naught A. So at the entry. Okay, so this is how we define the pressure recovery. So if you do this one, so I have 98 kilopascal divided by 100 kilopascal. So kilopascal unit get cancels. So 98 by 100 is going to be 0.98. They are asking you to write in accurate to 2 decimal places. Please make sure you are putting your answer in a way which in a way how it is asked, right? So it is 0.98. Right. Why this pressure recovery is important, especially for intakes, the losses what you can um, see is a total pressure loss or stagnation pressure loss. It is directly related to your entropy rise. How? Because we assume these ducts to be behave as isentropic in an ideal condition, or at least we model it as an adiabatic process. So we know for an adiabatic process, the total temperature going to be constant. Again, this is very, very important definition, the total property, the total temperature. The moment when I say this, the inherent assumption which comes along with this is the flow is steady, no body force, and no frictional losses as per when we consider the energy equation. We don't consider the effect of friction. That means no diffusion absent. And we are also introducing calorically perfect gas. So this is how we actually define the total temperature. So if it is not defined in this way, I cannot say T naught is constant. The study process is very, very important, and no body forces involved. So these are the things which can actually change the total temperature. So whenever I define total temperature is constant in a flow field, I am inherently assuming this is the flow field I am referring to. The last one is adiabatic. Okay, so important. Like I cannot just stop by saying it is the temperature of the fluid particle which would experience when it comes to rest. It is not full definition. It's the temperature of the fluid particle when it comes to rest in an adiabatic steady flow field with no body forces involved, or a calorically perfect gas. Then I can say the total temperature is constant in such flows. Okay, so yeah, so then why this is important, the total pressure loss, because it directly quantifies the rise in entropy of the system. How? Because if you look at my S2 minus S1 for calorically perfect gas equation, I can write something like Cp ln of T02 by T01 minus R ln of P02 by P01. So for adiabatic flow field with steady assumption, so this part T02 is equal to T01. So ln of 1 is equal to 0. So this part vanishes. So it directly says ln of P02 by P01 to the power of minus um, R by Cp, kind of thing, right? So it gives me an idea about how much of entropy change is happening, right? So that is why this quantifies the irreversibilities in the system. So that is why we are interested in the total pressure change due to irreversibilities in the system, right? Okay, so let us move on to the next question. That is, a combustor is operating with a fuel air ratio of 0.03. If the stoichiometric fuel air ratio of this is fuel used is 0.06, the equivalence ratio of the combustor will be. Can anybody say it quickly? 0? No. 0.5. Yes, that's correct. But let us see. So what is equivalence ratio? Equivalence ratio can be defined as the ratio of the stoichiometric fuel to air ratio, sorry, actual fuel to air ratio to stoichiometric fuel to air ratio, right? So if you look at this one, we have 0.03 divided by 0.06, it will be like 1 by 2, it is 0.5, accurate to 2 decimal places, so 0.50. So this is how we are going to put the answer. So now it's fine, it's a very straightforward question. We answered. What actually equivalence ratio signifies to us? So F actual is the actual fuel to air ratio. Say I have a combustor, I am supplying some amount of fuel and I have some amount of mass flow rate of air which is coming into the combustor. If I take the ratio of these two, that is my actual fuel to air ratio. What is stoichiometric fuel to air ratio? So if I have some kind of a fuel, say CXHY, carbohydrates, so then I am burning it with air, which is a combination of oxygen and nitrogen with 21% of oxygen and 79% of nitrogen within it. So, which would give me the combustion products, that is CO2 plus H2O plus the nitrogen as it is, it recovers. So, X CO2 plus y by 2 H2O. So that gives me x plus y by 4 times N2 times 3.76. So I have to add x plus y by 4 amount of air to combust it completely. So it's a chemical balance. So it doesn't matter what fuel or what air ratio you're actually sending in. So the stoichiometric is kind of a theoretical value you need to combust a given amount of fuel. So this is how you actually define the stoichiometric fuel to air ratio, like summation of molecular weight of the components of fuel times the number of moles of component of fuels. So say it is for fuel to summation of molecular weight of the components of air times number of moles of components of air. So this is how we define the stoichiometric fuel to air ratio. So the equivalence ratio says me, compared to my stoichiometric ratio, whether I am supplying the sufficient air to combust a given amount of fuel or whether I am supplying a less amount of air than the required, or and whether I am supplying a more amount of air than the required. That is what the equivalence ratio specifies. We call fuel lean combustion or fuel rich combustion based on the equivalence ratio. So for equivalence ratio greater than 1, equivalence ratio less than 1, we call like that, right? So what is a fuel lean combustion? It is the case on which we are supplying more air compared to required amount of the air. Whereas fuel rich combustion, where we are having a fuel which is the quantity of air which we are supplying to burn a given amount of fuel is not sufficient to make a stoichiometric combustion. So we are supplying a less air, say like x plus y by 4. I am just sending a fraction of that, say 0.5 times x plus y by 4. So I am not sending exactly x plus y by 4. So in this case, I have a fuel rich combustion because fuel is not going to burn completely in this case. The other case, again, fuel might not able to burn completely if I send the more amount of oxygen, fuel lean combustion, say 1.2 times. In that case, again, the combustion byproducts might be different. So stoichiometry is the exact proportion what we need to have a complete combustion. Okay, so this kind of gives a sense whether we are supplying sufficient air or less air or more air, right? Okay, jump to the next question, that is, an aircraft with turbojet engine flies at a velocity of 100 meter per second. If the jet exhaust velocity is 300 meter per second, propulsive efficiency of the engine assuming a negligible fuel air ratio is? So again, very straightforward question. So this we also discussed in our class. So how do we define a propulsive efficiency for a jet engine? So 2 alpha divided by 1 plus alpha, right? So what is alpha? Alpha is a ratio of forward speed to jet velocity, right? So in this scenario, the forward speed is given as 100 meter per second CI, and the jet velocity is given to be 300 meter per second. So alpha is going to be 1 by 3. So if I use that one, 2 into 1 divided by 3 divided by 1 plus 1 divided by 3, right? So it is going to be 2 by 3 divided by 3 plus 1, 4 by 3. So 3 get cancels. It is going to be 2 by 4. It is 0.5. So option B, 0.50, right? What's the difference between propulsive efficiency and the propeller efficiency? Luckily, we have one question on propeller efficiencies also. Propulsive efficiency is a measure on like how much of kinetic energy you are getting out of your fuel combustion is useful in producing the thrust. So if you look at the definition of propulsive efficiency, how do you define it? It is the forward thrust or the thrust power is actually thrust power to kinetic energy of the or kinetic energy uh, of the engine output, something like that, right? Output kinetic energy of the engine. So thrust power is nothing but thrust times the forward speed divided by kinetic energy can be written as half times assuming negligible fuel to air ratio. So I can safely take m dot of A is much larger than m dot of F. So I am assuming m dot of A is nearly equal, gas is nearly equal to m dot of A only. So I can write like Cj square minus Ci square. This is my kinetic energy, output kinetic energy of the engine. So if I use that one, what is thrust again? It is again mass flow rate of A times Cj minus Ci. That's the momentum thrust times Ci. I am actually neglecting pressure thrust for the definition purpose. Half of m dot A times Cj square minus Ci square. So again, this can be written as A square minus B square. So A plus B into A minus B form. A minus B form get cancels from numerator and denominator. So I am left with something like m dot A cancels. So Ci divided by half of Cj plus Ci. So that is what we have here, right? So this becomes, if I take Cj outside, it becomes Ci by Cj, 1 plus Ci by Cj. I am defining it as alpha. This is my propulsive efficiency, which talks about thrust power to the output power. Whereas the propeller efficiency, it is more related to the transmission of the energy from the shaft to the propeller, which is used for the thrust generation, right? Is purely defined for a turbo like propeller driven engines where shaft is rotating the propellers. So I will come to that point when I come to the question on the propeller efficiency. So here I have a propeller efficiency question. An aircraft with a turboprop engine produces a thrust of 500 Newton and flies at 100 meter per second. If the propeller efficiency is 0.5, the shaft power produced by the engine is. See now, I have a propeller driven aircraft which is actually connected to a turbo shaft engine. Say I have a shaft which is run by turbine or something. So which is delivering a power to run this shaft. This indeed this shaft is running the propeller, right? So now there is a transmission from the shaft to the propeller, there can be a loss in the while transmitting the energy from shaft to the propeller. So now this propeller is used to produce the thrust. So now if I look at the thrust which is produced, so thrust power to the power you supply to rotate the propeller which is producing the thrust, that is the shaft power. So that is called propeller efficiency. Clear? Yes. So now already we discussed it. So if you look at now, so it is producing the 500 Newton of thrust and flies at 100 meter per second. So what is the thrust power? This is the thrust times the forward speed of the aircraft divided by shaft power. What is the shaft power? We don't know, that we are going to calculate. So let us keep it as SF. So but the efficiency of the propeller is given to be 0.5. So if I use that one, so I can calculate shaft power is equal to thrust is 500 into 100 divided by 0.5. So it is going to be 5 into 100 into 100, that is 10 to the power of 4 divided by 5 into 10 to the power of minus 1. So cancels, it is going to be 10 to the power of 3. So it's going to be, 10 to the power of 4 plus 1, 5. So it's going to be 100 kilowatt, right? Option B. Okay. So now we are moving on to the next question. That is, an axial compressor that generates a stagnation pressure ratio of 4.0 operates with inlet and exit stagnation temperature of 300 Kelvin and 480 Kelvin respectively. If the ratio of the specific heat gamma is 1.4, the isentropic efficiency of the compressor is. Again, it's a very straightforward question. So if I look at my, so some axial flow compressor is given. Right, so they are given, so control volume, so I am just drawing. So they are given the inlet condition T01 is 300 Kelvin and exit stagnation pressure, so T02 is going to be 480 Kelvin, and efficiency of the compressor they are asking, and they are given this compressor produce the overall pressure ratio of around 4.0. So now, so if I look at my TS diagram very carefully, so I have a state 1 at P01 and it is rising to P02. That is my pressure ratio P02 to P01 in an actual process, some adiabatic process. Right? So that the actual process is such that the rise in entropy can be seen. So there is a rise in entropy of the system. Delta S is greater than 0. So that is how process has to take place. Now, this is my actual temperature at the exit, right? So this is my actual temperature at the inlet T01. This is my actual temperature at the exit. So this is giving me P02 at the exit of the compressor. So now, so if we know this pressure curves in a TS diagrams are diverging. So if I trace back this pressure curve, constant pressure line on a TS diagram, so I can extend in both the sides the constant pressure lines on a TS diagram. So now if I see where the pressure curve exactly intersects the constant entropy line, where I have S1 at the start of the process, or at the state 1, S1. So if I assume it to be happen in an isentropic way, that means the entropy is not changing, where this pressure curve would have been met. So that gives me the ideal work which is actually needed to rise the same pressure through an isentropic process. So I call this condition to be T02 dash. This is not actual, it's a virtual point on the TS diagram. What if my process is taken isentropically instead of adiabatically? So what is the work done needed to raise the pressure from P01 to P02? Ideally, that's what this point represents, this difference T02 dash by T01. But we know for practical reasons, the actual process is taking a little bit higher temperature difference to overcome the losses, right? So that is why if I want to define my efficiency of the compressor is going to be T02 dash minus T01 divided by T02 minus T01. This is actually the enthalpy change in an ideal way to enthalpy change in an actual process. That's what the work done is represented by. Since we are treating it is calorically perfect gas, I can take Cp out and cancel it out. So H naught can be written as Cpt naught. So I can take this Cp out, so I can cancel it out. So I can just represent in terms of temperature difference, right? So now, since this T02 dash and T01 both falls on a constant entropy line. So now if I use this S2 minus S1 relation is equal to Cp times ln of T02 by T01 minus R ln of P02 by P01. So I can write for S2 minus S1 to be 0, no change in entropy. So then this becomes T02 by T01 is equal to P02 by P01 to the power of R by Cp, that is going to be gamma minus 1 by gamma, right? So we know this relation, Cp minus Cv is equal to R. So if I write Cp by Cv minus 1 is equal to R divided by Cv, I can write Cv and Cp in terms of gamma and R itself. So I can show Cp is nothing but gamma R by gamma minus 1. Cv is nothing but R divided by gamma minus 1, like that. So if I use that condition, so this this can be shown as T02 by T01 as P02 by P01 to the power of gamma minus 1 by gamma. So now, see in this case where my entropy is not changing, that is between point T02 dash to T01. So I can use the isentropic relation only for these variables which is falling on constant entropy line. So I can use this relation. This note here, this is an virtual point, whereas P02 is actual pressure at the exit of the compressor. So I can relate this virtual point through a actual pressure rise in the compressor. So that's what we are using here. So efficiency can now be written as, if I take T01 outside, it becomes T02 dash divided by T01 minus 1 divided by T02 minus T01. So this is the actual temperature change. This is an ideal change. So now T01, so this both points are falling on the constant entropy line. So I can easily write it to be P02 by P01 to the power of gamma minus 1 by gamma minus 1 whole divided by T02 minus T01. So what is P02 by P01? That is the pressure ratio of the compressor that is given in the problem. So I can write pressure ratio represented by pi c gamma minus 1 by gamma minus 1 whole divided by T02 minus T01. So now put all the numbers given in the problem. So T01 is 300, is 4, gamma is 1.4, T02 is 490, 480. Okay, so if you put that number, you should be able to get 80%, around 80, 81. It gives me around 0.8099. So I can roughly make it 0.81 approximate value. So option B. right? It's not percentage, it's direct number. If you want to put it in a percentage, it will be 81%. So, but since the option is given in fraction, so we can directly put it in fraction, right? So straightforward. Okay, now I have a question on axial flow compressor again. An axial compressor rotor with 50% degree of reaction operates with an axial velocity of 200 meter per second. Absolute flow angle at the inlet of the rotor is 22 degree with reference to the axial direction. If the axial velocity is assumed to remain constant through the rotor, the magnitude of the relative velocity in meter per second at the rotor exit is. Very good question. So I have a axial flow compressor stage. Say I have one one rotor I am taking, which is rotating in this direction with velocity u, say. So I have a flow which is coming, absolute flow, which is coming at an angle with respect to axial velocity CA, that is alpha 1, which is given to be 22 degree. So that is given in the question. So now since it is already rotating, so I have a well-known vector relation, that is C is equal to U plus the relative component W. So to make sure this is already rotating at U, so the blade cannot see the flow at this absolute velocity vector, but it sees at an angle relative to the axial velocity. So given by relative velocity component, and the angle is beta 1. So my inlet velocity triangle something looks like this. U, C, W. So you see the vector relation W plus U is equal to C. That's the vector summation, right? So now axial component, the axial component is going to be remain constant for this stage. So with reference to this one, this is alpha 1 and this is beta 1. So sometimes referred as absolute air angles. This is the relative angle or the blade angle, right? So now at the exit of the stage, again I can draw one more velocity triangle considering all three velocity components U, C, which leaves with reference to blade with an angle W2. So I have again CA over here, which is going to be constant. That's what they are given, right? Axial velocity is assumed to remain constant through the rotor. So no problem. So now this is going to be alpha 2. This is going to be beta 2. So now they are also given one more constraint, that is axial compressor rotor with 50% degree of reaction. So what is 50% degree of reaction? So from the 50% degree of reaction, we can easily show that. So if I have a degree of reaction, that can be written as 5 by 2 tan beta 1 plus tan beta 2, or I can also write R is equal to 1 by 2 plus 5 by 2 times tan alpha 1 minus tan beta 2 kind of way. So it's minus, I guess, yeah. So for 50%, it is going to be 1 by 2. So 1 by 2, 1 by 2 get cancels. So I am left with alpha 1 is equal to beta 2. So it is going to be symmetric velocity triangle. That means C1 will become W2 in the exit velocity triangle. The magnitude is going to be same, and W1 in inlet velocity triangle will be equal to the magnitude of the absolute velocity at the exit velocity triangle. Also alpha 1 becomes beta 2 and alpha 2 becomes beta 1. So this is how the velocity triangle relations looks like. So we can easily use that one. So what they are asking is to calculate the relative velocity at the rotor exit. So they are asking W2. So either I can directly go to W2 calculation, or if I calculate C1, that is also fine. That is equal to W2. So you can approach this problem in multiple way. So let me approach in a way that what is given. So I know what is alpha 1. I know what is axial velocity, that is CA, 200 meter per second. So I know CA, I know alpha 1. So from these two information, I can easily calculate C1 using trigonometric relation. So say I just draw that part. So I know what is C1. I don't know. I can calculate. I know what is CA and I know what is alpha 1. So if I define the cosine of this angle, so cos alpha 1 can be written as CA divided by C1. So from here I can calculate C1 is equal to CA divided by cos alpha 1. So CA is 200, alpha 1 is 22 degrees. So cos 22. So if I use this one, so I should be able to get the relative velocity component. That is going to be 215.7 something meter per second is a magnitude. So because it's a 50% reaction, so W2 is also equal to C1, so which is going to be 215.7 meter per second. So let us just look back the question again. Accurate to 1 decimal places, so it is fine. 0.7 in meter per second unit. Right? So everybody clear? Yes. So very straightforward question. Right. So now we'll go to the next question. That is, the relative velocity of air leaving a straight radial impeller of a centrifugal compressor is 100 meter per second. If the impeller tip speed is 200 meter per second, for a slip-free operation, the absolute velocity in meter per second at the impeller exit is. Again, it's a straightforward question. So say I have a radial impeller, they are already given straight radial impeller, right? So I have a impeller disc. So I have multiple impeller blades. Say the relative velocity is nothing but the velocity at which the flow leaves the impeller relative to the impeller geometry. So it is going to be W2 at the impeller exit, and it is also rotating with some velocity U at the radial distance R from the axis. So if I want to calculate, U is going to be omega cross R, right? So that is how they are related. So omega is the rotational speed of the impeller disc. It's angular velocity, right? So if it is already rotating at U and flow is leaving at a relative velocity of W, so then my absolute velocity is again going to be C is equal to U plus W. So if I have to draw the velocity triangle for this one, so I have U in this direction, W in this direction. Where does my C direction looks like? It has to look something like this, right? This is my absolute velocity vector direction. So now we know it is a slip free operation. If there is a slip, then what happens? My relative velocity will be little bit off from this radial direction because it's not exactly going to be radial. So in this case, I have W2 is equal to CR at the exit. But in a slip, if there is a slip that is actually coming from the inertia of the fluid, so then my velocity triangle something looks like this, because U is not going to change. It is always going to be omega cross R. It is dictated by the angular velocity and the height at which we are operating. U is going to be same. Radial velocity vector is also not going to change. It's governed by our physics. And the only thing which can change is my W velocity vector is going to readjust. So that means W2 is in this direction, CR2 in this direction. So my absolute velocity vector is now going to change because it is governed dictated by this equation. If W is changing, C is also changing, though U is same. So but the thing here is my component of velocity is going to be different, CT, right? So that is going to change. Fine. So now you don't have to worry about this part because they are already given. It's a slip free operation. So my W2 is CR2 and I have U at the impeller tip. They are asking me to calculate the absolute velocity at the impeller exit. So I can easily calculate because it's a Pythagorean triplet now. It's a 90-degree at which it's a straight radial impeller. So beta is going to be 90-degree for this case. So now I can easily calculate C is equal to square root of U2 square plus W2 square. It's actually CR2 square, but CR2 is nothing but W2 in this case. Okay, so you put that one. U2 is given 200 meter per second and the radial velocity is also given 100 meter per second. So if you put that one, you should be able to get 223.607 something, but they're asking you to accurate to one decimal places. So if I have to accurate to this one, it is going to be 223.6 meter per second. Okay, so everybody clear with this, right? Okay, somebody is asking me to go to the previous question. So you mean this question number 8? Yes, I suppose your name Vix only. Okay, so this question is asking me to calculate the relative velocity, and they are also given 50% reaction stage. For 50% reaction stage, the the velocity triangle at the entry and exit to be symmetric. So the magnitude of absolute at the entry triangle is same as the magnitude of velocity at the relative velocity at the exit triangle. So if I calculate this one, I am actually calculating this one also. So I can directly take that as an answer. Okay. Or else you can treat alpha 1 is equal to beta 2. Then again you can calculate directly over here cos beta 2 equal to CA divided by W2. Again it is going to be CA divided by cos beta 2 is W2. Again you will get same answer. I told you I can approach this problem in multiple ways. As long as you are understanding the problem correctly, and you are doing your math and physics right, you are going to end up in the correct answer. Okay, irrespective of the approach you are taking. Some might take longer, some might take faster. In terms of numbers you are putting in virtual calculator, some can take much more time, but still you can get the answers. Okay. Okay. So that ends our discussion on 2018 gate paper on jet propulsion topic. So if you guys have any questions or doubts, you can ask now. It's like thank you uh, for the for your attention.